Have you started recording? Thanks. All right, how are you guys doing? So a couple thumbs up, that's fantastic. You know, if you're ever having a bad day, I don't want this to come across to, for you to have a pity party on me, but about 3 weeks ago, so if you're ever having a bad day, you can think about me. This is my new problem I have in my life. About 3 weeks ago, I was sitting in my office, and it was shortly after I turned 45. It had been the day of, I don't know. But I'm sitting in my office, and I start hearing this ringing in my ears. And I was like, what is that? And I thought it was my printer or my computer. And when I plugged my ears, it was still there. Since that day, my ears have not stopped ringing. I'm going to have this probably for the rest of my life, or until I go deaf, I don't know. But very common as you get older that you get, it's called tinnitus or something like that, just constant ringing in your ears. And so if you're having a bad day, you can just think, at least I'm not like Brother Corey that has constant ringing in his ears. So it's not too loud, but when things start to, when there's not a lot going on noise-wise, it grabs my attention. It's hard for me to sleep with it going on. But, okay, let's start off with a prayer. I'd like to offer a prayer for us. Thank you.
It's not gonna.
Amen. Thank you. Before we get started, any comments about Elder Cook's devotional? It's about the response I got from the last class. Anyone watch it or listen to it? Okay, a few of you. Just no comments about it? Go ahead. Yeah, that was cool. So that comment was, he liked how he said we are living in a sacred and a holy time. It's easy to think that with all the stuff that's going around that it's not sacred and holy. He did talk about how we live in the world, but we don't have to be of the world because we don't have to engage in those kind of worldly activities and thoughts and ideas. So nice. Yes. Yeah. All right, thank you. So that comment was about, he liked that he'd have great expectations for us, that from his drawing on his 80 years of wisdom, he had great expectations that we could remain on the covenant path and take that all that Heavenly Father has in store for us by doing so. Where did he say that happiness was most likely to be found, or the greatest happiness is found? In the family. So I was listening to a podcast yesterday on my way home from work, and it was actually about political philosophy. So it went more detailed than this, but the guy talked about how hundreds of years ago, a few hundred years ago, when the idea of freedom was first thought of, the idea was that people would be free to live according to what they thought was the good life, like make their choices of what they thought was good. And he said the idea of freedom has changed to eliminate the part of good choices out of that. And now it's free from just restrictions to do what I want. And so the talk was about how as we've moved more towards that freedom, that we've lost the institutions that teach people what good choices are and what bad choices are, and that's caused, of course, all sorts of problems in our society. And it was almost exactly the points he was making was almost exactly what Elder Christofferson talked about in the last conference. So like all those same points. So it was quite interesting. Nice to have a prophet and prophets, inspired men that tell us what's truth. I didn't have to be like the moderator on the podcast trying to figure out if this was true or not, right? Like, oh, it was just some guy's idea. Well, we have more than just some guy's idea. It's nice. Okay, so there's a couple problems up here. These are from practice exams. I think it's from the third practice exam that's listed on Learning Suite. So if you've got that far in your study, these may look familiar. So take a few minutes and work on these. Some of the work on that first one is up here, but try to do what you can. Try to do what you can without looking at it, and then we'll start going over these. And then after we do these two, we'll take questions, any questions you guys have that you want to talk about in preparation for the exam. Before I quit, though, I should say the homework is up. So next time we have 5.1, so a new section, starting a new chapter on orthogonal matrices and orthogonality. So read the chapter, watch the video, and do the 5.1 web assign. I'm trying to get the pre-class videos up quicker. On the survey, some of you guys mentioned that you'd like to have them up quicker. So this one's been up for a couple days. I'll get the next one up hopefully today, if not tomorrow. So, and study hard for the exam. We only have 3 days in person after this class. It's kind of amazing. Yes? No, the exam is not yet up on Gradescope. It'll show up tomorrow morning, probably 6 o'clock. So I haven't set that yet, but the plan is 6 in the morning. I could make it at midnight if you want. I just don't anticipate anyone wanting to take it that early. And it runs through Friday? Yep. Yeah, so the exam, so this is the last point over there. Exam 2 runs Wednesday through Friday. It'll be on Gradescope. Same situation as last time. You're on your honor not to use internet, notes, textbooks, calculators of any kind, phones, etc. It's testing center conditions with you, scratch paper, and the exam. Well, you can use your phone to take a picture of your solutions and upload it. So, yeah, similar to last time. Other questions about the exam? Yes. I think it's about the same number of problems, but just because this material is a little bit more advanced and some of the computations take longer, I think it's going to be a little bit longer. So I'm planning on making it. We're putting on a time limit just so you don't spend more of your time than you need to on this. So last time 4 hours. I think I'll do a 4.5 this time, just to make sure. You guys still have plenty of productive time to work on it. So, okay. Yes. Oh, have I received any hilarious comments from like the survey that I sent out? I've read through almost all of them. Nothing jumps out to me as hilarious, but Porter, did you see any that? Yeah.
I asked my TA for another class, and one of the comments the students gave was, "I learn a lot from lectures as long as professor is sober."
Oh, so that comment for those online was hearing from another class, and one of the comments was, "I learn a lot from lecture as long as the professor is sober." So, one of my teachers here, she went to Utah State, and she's retired now, so this is quite long ago. And the students would be making bets about whether the ashes on his cigarettes would fall on the floor before he could knock them into the dust tray. So they'd smoke in class, and they would just use the dust tray on the chalkboard for their ashtray. So very different world than we live in now. So, Okay, so take a few more minutes to work on these problems. If you have questions, just raise your hand. I'll come on over. Okay, I'm going to start walking through this. If you're good with the beginning, just keep working on. So if I want to know, if I want to find it, if I want to diagonalize a matrix, the first thing I want to do is find the eigenvalues, because the entries of the diagonal matrix are the eigenvalues. And I want to be able to write this. I want to be able to write 1, a minus 3, a minus 3, 0, a minus 5, a minus 6, 0, 3, 4. I want to be able to write this as some invertible matrix times some diagonal matrix. And these diagonal entries here are the eigenvalues. And then I have to have this. So this is D, this is P, and here this is P inverse. So I don't have to find P inverse for this problem. It just asks for the D and the P for the diagonalizable matrix. But I have to find the eigenvalues first. So let's do that. So I subtract lambda off the diagonal. And I'm going to find the determinant. And it's a little easier, I think, if you factor expansion, because you have this one row with two zeros. So you get 1 minus lambda times this determinant here. So you get a -5 minus lambda and 4 minus lambda. So that's that diagonal, minus a -18. So you get +18. So if you expand this, combine your -20 and your 18, it simplifies to lambda squared plus lambda minus 2. And I also have this factor here, 1 minus lambda. And when I did this in the last class, I foolishly, I'm embarrassed to say, I multiplied all those together and had a cubic. And then I was sitting in my cubic. I'm like, why did they have us factor down a cubic? And although I could, I was like, this doesn't seem like they should put something on the exam like this. So why was that foolish of me? So because it was already partially factored. Yeah, so why multiply together if you're going to have to factor down? So that was foolish of me. And then I was like, oh yeah. So you guys don't get to see half the mistakes I make, because I get the run through with the 1 o'clock class. So I factor this one down. You can factor it down to lambda plus 2 and lambda minus 1, and oh yeah, so there's my 1 minus lambda. You can, if you want, rewrite this as lambda minus 1 and pull out the negative. So I was more comfortable with that, so that's what I did. But either way, the value that you plug in to make this 0, because really we want to know, when does this whole thing equal 0, right? The value that you plug in either one of these, the lambda to make 0 is 1. So here, this one, we get 1 as a solution. This one, we get 1 as a solution. This one, we get a -2 as a solution. So we have our 3 eigenvalues. In a 3 by 3, you'll always have 3 eigenvalues. It's just some that might be repeated. And sometimes it might be 0, but you'll always have 3. So here we have 1 that has an algebraic multiplicity. Lambda equals 1 has an algebraic multiplicity of 2. Okay, any questions? Yes, Ian. That's right. So say. That's right. So Ian was emphasizing that it doesn't matter which order we put these in the diagonal. We can choose whichever order they want. The key is that the eigenvectors, the columns of P, which will be the eigenvectors, they have to match up in the same order as our corresponding eigenvalues. So here, I need to put one of my eigenvectors for 1 here in the middle, my other eigenvector for 1 here. I put my eigenvector for -2. And it doesn't matter on the first 2, since these are both 1, it doesn't matter which way. I'm assuming we'll get 2 out. But yes. Other questions or comments so far? Okay. So we have our eigenvalues. How do we find our eigenvectors? We subtract our eigenvectors off the diagonals, and then we look for the null space of that matrix. So the null space is all the vectors we can multiply by that matrix to get 0, so we can set up the system. So I first started with 1. So I subtracted 1 down the diagonal. I get this. You can easily row reduce and see these are just copies of this or multiples of those. So you can put down your bottom 2 rows of zeros, divide by a -3 here, and you get this system. And so here I have 2 free variables. This is I only have 1 pivot position in this whole matrix. It's just this one. So right here. So I have a free variable here, I have a free variable here. So x and z's are free variables. So when I wrote down the system, so this means I have 1y plus 1z equals 0. So I wrote that down, and since x is a free variable, I wrote down x equals x. Since z is a free variable, I wrote z equals z. And then I wrote this down as this in vector form. And I have some x's and some z's over here, so I'm going to split those up. And it's nice. Why? We'll talk about in a second. So I took my 1x, 0, 0, and these, I have a -1z and 1z's. I pulled out my x's and z's, called them t's and s's. So I renamed these so that I have parameters that aren't connected to x and z. And these are my 2 eigenvectors associated with lambda equals 1. Now, if the question asked, is this matrix diagonalizable? What's the earliest place I could stop and know that it's diagonalizable? I could stop right here. I could actually stop before. I don't have to look at this one. This one, every eigenvalue has at least 1 eigenvector. And so I know I'm going to have at least 1 eigenvector here. How many eigenvectors do I need for this to be diagonalizable? As many as I have eigenvalues. I need 3. This is a 3 by 3 matrix that I'm trying to diagonalize. This I need to have a 3 by 3 matrix, so I need to have 3 linearly independent eigenvectors here. So every eigenvalue is going to have at least 1. So this one, this -2, I know I'm going to get 1 there, no matter what. Okay? If you have an algebraic multiplicity of 1, your geometric multiplicity will always be 1. The problems come when you start to have algebraic multiplicity of 2 or more, because then you might get a geometric multiplicity that's less. But you will always have a geometric multiplicity of at least 1. Yes? That's right. So as soon as I get to here and I see that, hey, I have 1 pivot position and 2 free variables, then I know that I'm going to get 2 vectors out as the basis for the null space associated with lambda equals 1. I know I'm going to have 1 here with lambda equals -2, because you're going to have at least 1 all the time. So then I get 3 and I'm good. So I could have stopped right there if that's what the question asked. So questions about that? Okay. So I have to do more than that here. I actually have to find P. I have two of my columns though. So I could start by building P. I could do 1, 0, 0 and 0, a -1, 1. So these are the eigenvectors with lambda equals 1. So, but I still need to figure out what the eigenvector is for lambda equals 2. Sorry, lambda equals a -2. So I subtract off a -2, which is the same as adding a -2 down the diagonal. I get this matrix. I row reduce. This is easy down here because they're multiples of each other, so I know I can make that bottom row 0. Divide by my leading values. I do add this row to this one to make that 0. That ends up being 1. I get this. How many free variables do I have? 1. Just z's here. And so that says x plus z equals 0 and y plus z equals 0, and z is a free variable, so z equals whatever I want. And so go ahead and solve. So x equals a negative z, y equals a negative, oops, I made a mistake, 2z. So negative 2z, z equals z. So that means any vector of the form, I'm going to replace z on my right with t parameter. So then I can do a -1. It looks like one of my lambdas, a -1, a -2, and 1. So questions about that? Yes? Yes. So that question was, when you're row reducing, do you want to row reduce as much as you can every single time? Yes, you do. So I should have a really good reason for you. If you don't, like in this case, if you keep this -1 here, you're going to have a y. And you're going to have a y on this side over here, and you're going to think you have a two-dimensional space, right? So when really you don't, like you shouldn't. So, okay, so now I can take this and put it right here, a -1, a -2, 1. So this is the eigenvector for lambda equals 2, -2. And so here's my p, here's my d, and then I could find the inverse of that and put it there if they asked me to. Questions on diagonalization? Great. Okay, that was, yes. No, it doesn't matter if P and P inverse are switched. Like from the definition, you still found P inverse is still an invertible matrix, and P is still an invertible matrix, so it doesn't matter. Different books write it different ways. Yeah, so no. Okay. Yeah, if we labeled this as P, so the one with your eigenvectors should be on the left, but you could call this one over here P, and then this one would be P inverse. But I think you always want the ones with the eigenvectors here on your left, I believe. Okay. Let's pull up that thing. Yep. Okay, so I know not all of you got to look at the second problem, which says 7. So take a minute, look at those, and then take another couple of minutes to talk about those to your neighbor, about whether those are true or not. Which of the following facts must be true, and talk about why they must be true. So. All right, let's come together. Yeah, yeah, yeah. It'll be a grand old time. Or that, so however that song goes. All right. Okay, so let's just do thumbs up and thumbs down. Okay, there's no thumb sideways on this. Okay, there's no partial truths. Interestingly, I have a book because since we were kind of talking about what is true at the beginning of class, it's common for scientists or social scientists to say that there is no such thing as absolute truth. And I have a book that says that. It's an education book that says there is no such thing as absolute truth. Why can that not be true? Because that would be an absolute truth. Right, so they're saying it, they're of course saying that, oh, this is an absolute truth. But so kind of ironic that they say that there's no such thing as absolute truth. But if that was true, then that would be an absolute truth. So it cannot be a true statement. So, all right. Okay, so thumbs up, thumbs down. The matrix A minus I is invertible. True is up, false is down. Okay, I see lots of thumbs down, a few thumbs up. Okay, someone that put their thumbs down, someone that put their thumb down, you didn't have to put both. Someone that put their thumb down, why would you say the matrix A minus I is invertible, Ryan? Or, yeah. Okay, so this is, if you think of taking A minus 1I, then we do know that 1 is an eigenvalue. And so we know, since it's an eigenvalue, A minus 1I needs to have a determinant of 0. Like, as we find the eigenvalues so that the determinant of A minus the lambda I are 0. So we want those determinants to be 0. If the determinant is 0 of a matrix, then is it invertible? It's not invertible. The determinant is 0, it's not invertible. If it's not invertible, the determinant is 0. Okay? So the matrix A minus I is, it's false that the matrix A minus I is invertible. Okay? The eigenvalues, so the intuitive idea of the eigenvalues is it's a stretching, there's some direction that stretches or shrinks by that factor when you multiply by A, right? The constant A times the x vector is the same as multiplying by a constant times the x vector. If that's the case, then this is true. But the way we find eigenvalues and the way we find eigenvectors is we do a little of the algebra. We rewrite this as ax bar minus lambda ix. So this it doesn't need, this is just a vector, but in order for us to pull out the x over here, we're going to make this a matrix because we have to have a matrices minus matrices, otherwise it's not defined. So let's factor out that x bar, you get a minus lambda I times x bar. The way we find them is we find the values that you can subtract off the diagonal from A that make this non-invertible. Because we want non-zero x's, non-zero vectors that you can multiply by this matrix and get 0. And that only happens when you have a non-invertible matrix. So, okay. All right. So, all right. A itself is invertible. So thumbs up if you say it's true, thumbs down if you say it's false. So lots of thumbs ups, a couple thumbs downs. So I'm just going to talk through this. I know some of you could respond, but if you respond, then I have to restate it just for the people that are online anyway. So A is invertible because we do not have 0 as one of our eigenvalues. That's how we know that A is invertible. If A was non-invertible, then 0 would be one of the eigenvalues. Because that would mean we wouldn't have to change anything about the matrix. We could just have A minus 0i, which is just A times x bar. Well, we could get non-zero x's here to get 0. We'd have a null space that has some, we'd have a null space that was at least one dimensional here. So if that's the case, then then you'd have 0 as an eigenvalue. So questions? Yes? Oh, so that question was, he gets that if it's not invertible, let me see if I have it the right way, that if it's not invertible, you'll have an eigenvalue of 0. But if you have an eigenvalue of 0, does that guarantee that it's not invertible? Oh. Oh, right. Okay, so if you have a 0 as an eigenvalue, then you know it's not invertible, but could there be non-invertible matrices that don't have 0 as an eigenvalue? That's really what you want to know, right? It is an if and only if. You're guaranteed, if you're a non-invertible matrix, you will have an eigenvalue of 0. And of at least 1. And if you have an eigenvalue of 0, it is a non-invertible matrix. Those are equivalent statements. So it is one of the, on the invertible matrix theorem, that's one of the things that we end up adding is that lambda equals 0 is an eigenvalue of the matrix. So those are equivalent. So if none of the eigenvalues are 0, then it cannot be, then it is an invertible matrix. Yep, it's a guarantee. Yep, because it's invertible only if and only if you have 0 as an eigenvalue. So if you have 0 as an eigenvalue, it's invertible. If you don't have 0. I mean, it's not invertible. It is invertible. Yes, you're guaranteed. So since none of these are 0, we know that it's an invertible matrix. Good question. Other questions on this one? Okay. All right. Number 3, well, the third one down, it's not really numbered. The set of eigenvectors here are linearly independent. So thumbs up if you say it's true, thumbs down if you say it's false. So, thumbs on your phone if you're playing a game. So, okay, lots of thumbs up. Yes. There is there's a theorem in the book that says for any matrix, the set of eigenvectors is linearly independent. They're always linearly independent. So even if it just said V1, even if we only had 2 eigenvectors here, which is a possibility, well, it's not if we had 3 distinct values, but if it was 1, 1, 5 and it said, oh, we have eigenvectors V1 and V2, that set is linearly independent. So for any matrix, well, when you write down all the eigenvectors, that set, it's a linearly independent set. So, okay. Questions on that one? I don't have we haven't talked about like a really good reason, or we certainly haven't proved that in this class. The book does, but yes. Oh. So if you're proving on the test, then say, you might not know the number. You can just say, by a theorem in the book, we know that, and you can write what you know. Or we know that for similar matrices, the determinant of A equals the determinant of B. If A and B are similar, we know that. So you can just write it down that way. Good question. Yes. There certainly could be. Like there was a proof on the last one, right? You had to show that the dot product was equivalent to this other, a quarter of this dot product, a quarter of that dot. So certainly could be. So they're fair game. So nothing too crazy. So kind of like the proofs that that I emailed out last time, or the proofs you did on this last homework of proving that the determinant of, what was that problem? A and B are invertible. If A and B are similar, then and A is invertible, then B is invertible. So that one, that's an example. Easiest way to do that one, by the way, is to just use that the determinant of A. Okay. I know not all of you did this or struggled with this, so I'm just going to take a break and walk through this. So we know that if A and B are similar, we know that this is true, right? Because that's by definition. I actually don't even know if I need that. If A is invertible, then I know the determinant of A is not 0. And in theorem 4.22 whatever, the very first one says that if A and B are invertible, if A and B are similar, then the determinant of A equals the determinant of B. So the easiest argument here is to say, oh, well, if A is invertible, then I know the determinant isn't 0. And if A is similar to B, then by that theorem, I know that the determinant of A equals determinant of B. So I know the determinant of B is not 0. And so by the invertible matrix theorem, I know B is invertible. So that's like an example, but it's probably the easiest argument for that one. But even if you didn't do that proof, you could say, okay, if I know the determinant of A isn't 0, then I could do the determinant of both sides of this, determinant of A, determinant of PB, P inverse, and then you can do the same kind of stuff we did the other day in proving that the determinant of A equals the determinant of B. Well, I didn't do it in this class. I sent out the video afterwards. And you end up with the determinant of A equals determinant of B. So you know, hey, determinant of A is not 0, and that's the same as determinant of B. So the determinant of B is non-zero, it's invertible. So there's a couple different ways to do that. So if there are proofs on there, I imagine it'd be something like that. Okay. Where are we at? Oh, this one, fourth one down. The eigenvalues of A inverse are a -1, a -4, and a -5. Thumbs up if you say it's true, thumbs down if you say it's false. Okay. Nice. Okay. See them all thumbs down, those that were willing to vote. Yeah, the eigenvalues of A inverse these are the additive inverses, but they're the multiplicative inverses. So they should be 1, 1/4, and 1/5. And you can think about that as, if you think about the transformation that A does, it says there's 3 directions, and one, I don't change it at all. That corresponds to this stretching factor of 1. Another one, I stretch it by a factor of 4. Another direction, I stretch it by a factor of 5. If I undo that, which A inverse will do, then I have to shrink this same direction for the lambda 3. I have to shrink that by 1/5 to get back to this original length. And I have to shrink this one by 1/4. And I wouldn't change that one at all. So 1, 1/4, and 1/5 is what these should be. Questions on that? Okay. Eigenvalues of A transpose are 1, 4, and 5. Thumbs up if you say it's true, thumbs down if you say it's false. The thumbs I'm seeing are pointing up. Not seeing everybody's thumbs. That's true. The eigenvalues for A transpose are the same as A. You can clearly see it if it's a triangular or a diagonal matrix, right? So that might give you reason to say that it's true for the other ones. Okay, there is an invertible matrix P and a diagonal matrix D such that A equals PD P inverse. So this is saying it is true that A is diagonalizable. This is the definition of diagonalizable. So is A diagonalizable? Thumbs up if you say yes. Thumbs down if you say no. Lots of thumbs up. Nice. And the reason we know is we have 3 linearly independent eigenvectors. V1, V2, and V3. That's all we need. we also know by a theorem that if you have n distinct eigenvalues, you're guaranteed to be diagonalizable. If you don't have distinct eigenvalues, it still might be diagonalizable. It just doesn't guarantee that you're diagonalizable. But if you have distinct eigenvalues, then you're guaranteed to be diagonalizable, because for each of those eigenvalues, you know you'll get at least one. You know you will get you'll get one eigenvector, and so you'll have n eigenvectors. Eigenvectors are all linearly independent, so you'll be able to make your p vector with your p matrix with those columns as the eigenvectors. So good there. How about the last one? Determinant of a plus 4i equals 0. It's false. Yep. If it was a minus 4i, you'd be good because 4 is an eigenvalue. But this is what if this was minus 4, this would be true, or if this is negative, you'd be true. But you're off by a sign. Okay, we've got 30 seconds. What questions do you guys have? So sorry, I didn't mean for that to take so long. Yes.
So, like on the last one, if it was they did minus the eigenvalue of the inverse, it would still equal 0. It would, right?
Oh, so if it was like the determinant of a minus a fourth I, only if it was a inverse minus a fourth I.
Okay.
So 1/4 would be an eigenvalue of a inverse. So if it was a inverse minus a fourth I, yeah, that'd be a nice test question. Other questions? Yes.
What if you had 3 eigenvalues that were the same? Could you still get 3 eigenvectors, like unique eigenvectors?
Yes. Yeah, you could have 3 eigenvalues that are the same, and in a 3x3 matrix, you could have 3, and you still could be diagonalizable. You're not guaranteed it, though, but you still might be diagonalizable. So it's possible.
So
Yes.
if that was the case, like specifically in a 3x3 matrix, what would that look like? Because wouldn't we have to have three free variables in order for that to work?
Oh, yes, but you do, like, think of the identity matrix. If you subtract the ones off the diagonal, you get zeros, you just get columns of 0. So you do end up with 3 free variables. So that's right. Way to think through that, Gilbert. Nice job. Okay, have a great day. And take a moment for me just to listen to silence for a few minutes.